Good afternoon. Today we will start with the next topic, filter design by placement of poles and zeros. In our last lectures, we have already discussed about what are poles and what are zeros. Okay. So if you look into the transfer function over here, so what we have Hs equals to Ps by Qs, which are basically Ps is a polynomial, Qs is a polynomial. Then this Ps by Qs, it can be broken down into these functions where we have the roots of the numerator which are regarded as the zeros, and the roots of the denominators, they are regarded as the poles. Okay, apart from this polynomial, within this polynomial itself there is a constant multiplier which is combining both the numerator and the denominator. So what is this? This is regarded as the gain of the system. This is regarded as the gain of the system. Okay, now if you look into the figure 7.13a, so what happens over here? We all know about the vector representation. Suppose there are 2 points given in a plane, complex plane. Okay, so what happens? So one point is z and the another point is p, and there is a vector from which starts from z and ends at p. Then that vector is regarded as p minus z. Okay, similarly, if we replace these points, okay, suppose this point P, it is the point of interest for us, okay, and then we place the this poles and zeros over here, we will be having similar vectors to that point P. Will be having similar vectors to that point P. Okay, now when we talk about the filters, so what happens is that this point P of interest, it is on the imaginary axis. Okay, it is always on the imaginary axis. Why? Anyone? Why we are interested on the imaginary axis? Yes, it's a j omega. That means over there we are having the frequency components, and when we are designing any filters, we are interested only in the frequency response. We are only interested in the frequency response. Okay, that's why when we will be dealing with the filters, we will be looking into the point P when this point P varies from 0, and slowly we will increase it till we reach to the infinity. Okay, so if you look over here, so what happens? P minus z1, then P minus z2, P minus zn. In this way you get the equation. Now this distance from say pole to the point P, it is given by d1, and the angle is given by theta 1. Okay, similarly for pole to d2, theta 2. Likewise, when we go for the zeros, we have r1, phi 1. We are just denoting the distance is r1 or the length is r1 and angle is phi 1. Okay, so r2, phi 2. Okay, now if we try to solve this equation and put these values d1 theta 1, d2 theta 2, r1 phi 1, r2 phi 2 into the equation over here of Hs, which is basically the transfer function of the system or the filter, then we can write or rewrite that equation in this format Bn r1 into e to the power phi 1 r2 multiplied by phi 2. Let us ignore the other part, okay, because in the previous slide we are having two poles and two zeros. You can generalize the thing at a later stage. Okay, now if you look into this, r1 e to the power j phi 1, r2 e to the power j phi 2 divided by d1 e to the power j phi 1, uh, d2 e to the power j phi 2. Now again if you solve it, you can take out these real components, you get r1 r2 divided by d1 d2, right? And what happens to these five components? It becomes e to the power j phi 1 plus phi 2 minus of theta 1 plus theta 2. You're getting my point? So again, if you look into the modulus, that means the real part of the system, then it becomes Bn multiplied by R1 multiplied by R2 divided by D1 multiplied by D2. What is it? These are nothing but product of the distance of the zeros to the point P divided by product of the distance of poles to P. That means the length of the vectors of the pole position to a particular frequency, the product of all those lengths divided by product of all the lengths of the zeros divided by the product of all the lengths of the poles. Okay, so that gives us the amplitude response of the filter. That gives us the amplitude response of the filter. Okay, then similarly, if you want to find out the phase response, okay, so this phase response we have phi1 plus phi2 minus theta1 plus theta2, that is sum of zero angles to P and sum of pole angles to P. Okay, and what are these P's? The P is nothing but it is corresponding to the frequency, because I said when we were looking into the filter designing or any system designing aspects, this point P is in the y-axis, which corresponds to the omega. Okay, so over here, if you see at S equal to P, so the point P is varying. So P will be basically 0, 1, 2, 3, 4. Likewise, it will go up to infinity. So as we go towards the infinity, you will get all the frequency components, and then we need to plot in the amplitude plot. This would be your frequency. So at different points, you will be getting the different modulus of HS. So you will be getting some points like this, and likewise, you will be getting the amplitude response. So amplitude response is nothing but modulus of h of s divided by versus the omega. Okay, h of s versus omega. When you plot, then you get the amplitude response. Similarly, if it is the phase angle, then you get the phase response of the filter. Okay. Now let us take a single pole example. Okay, so you have to remember, when we are putting any pole or a zero somewhere, so there would be a conjugate pole and a zero. Okay, so for every conjugate for every pole or a zero that has been placed within the S plane, there would be a conjugate pole and a zero. Okay, now we have placed a pole over here. So if you see, we are having 0 and we are going towards the infinity over here. So if you see, we are having this D pole to this omega, j omega, it is the D. So it basically it starts with from 0. Okay, so it starts with from 0. So 1 by say D0, it will be a finite value, you get a finite thing. Now slowly when we are going towards this j omega point, so what is happening? Our response increases and it reaches a maxima at omega naught point. Why? Because h of s is inversely proportional to d. It is inversely proportional to the d. So when the distance of the pole to the omega naught, it is in the straight line, that means it will be having the shortest point, shortest distance, not point, it would be having the shortest distance, and since it would be having the shortest distance, the d will be small and 1 by d it will be high. Okay, that's why it reaches a maxima at omega naught, and thereafter as you move to omega plus omega naught plus delta omega, again if you see, the response starts falling down. Okay, similarly, if you try to plot this phase responses, you will find that you are getting this kind of phase. Okay, now what happens to this conjugate pole? The conjugate pole, if you see, 1 by S modulus, it will be given by D multiplied by D dash, say for example. Okay. Now if you look, in majority of the cases, this D dash value will be much higher. And if the D dash value is much higher, the effect on 1 by D is negligible. Hence, when we try to find out the filter response, usually we negate the effect of the conjugate pole or the zeros what we place into the system. Okay. So we do not consider this, and hence we consider that Hs is directly proportional, inversely proportional to 1 by D. Okay. The same logic, it applies over here in the case of 0 also. So what happens? So here if you see, the distance would be the somewhat large. So as we come towards the omega 0, the distance is shortening. So distance is getting shortened, right? So since in the case of 0, modulus of Hs is directly proportional to R, since the R is getting shortened, our amplitude response is also getting shortened, and it reaches a minima at omega naught, and thereafter the amplitude response increases. Similarly, we can look into the phase plot. In the case of pole, it varies from 0 to -pi, and over here it varies from 0 to pi. Okay. Now, there is another thing. Suppose we change the value of alpha. This is alpha. Okay. Now, suppose we have placed, say, this is P1, P2, P3. Okay. So what will happen? P1 to omega naught, it is having the shortest distance. So what will happen? Highest peak. P2 to omega naught, more, there will be a medium peak. P3 to omega naught, largest distance, you will be having the shortest peak. So what happens? As we are moving away from the frequency axis, the effect of the pole is reducing. In other words, we can say, as we move the pole towards the frequency axis, the effect of the pole increases. Okay. The same thing, it happens, suppose I am having Z1, Z2, Z3. In the case of Z1, R is the shortest. In the case of Z2, R2 will be bit higher, and in the case of the Z3, R3 will be much higher. Okay. So as we place a 0 away from the system, what happens? There is an increase. There is an increase in the amplitude response. Okay. Over here there was a decrease in the amplitude response. Over here there is an increase in the amplitude response. Okay. In other words, if we what is the what is the 0 meant for? 0 is meant for suppressing the signal. Okay. That means when the zeros are placed near to the pole, near to the say j omega axis or omega naught axis, the effect of the 0 would be pronounced. Okay. If you look into the amplitude thing, there is, if you go towards the P3, amplitude is decreasing. If you go to the towards the 0, amplitude is increasing. But if you look into the effect of the poles and the zeros, effects and the poles and the zeros are predominant when they are placed closer to the this frequency axis. When they are placed closer to the frequency axis. So this is the important thing that you need to know. Okay. There is another interesting parameter. What happens when we place a pole on a 0 and vice versa. When we place a pole on a 0 or vice versa, or we place a 0 on over a pole, what will happen? The thing is that when you the coordinates are same, B1 and R1, it would be same, and since they B1 and R1 will be same, one is in the numerator, one is in the denominator, it gets cancels out, and there would be no effect of the pole or the 0. Okay, so placing a pole over a 0 or vice versa cancels each other's effect. Cancels each other's effect. Now there is a rubber membrane concept. Okay, so it helps us in understanding how a filter may behave. Okay, in a qualitative aspect. Okay, in a qualitative aspect. Why I am interested in this one before going into the mathematics? The reason being, it gives you an understanding what type of filter response you should be expecting when you are putting a pole and a 0 in the plane, in the S plane or a Z plane. Okay, why this is important? This is important because whatever the mathematics you do, ultimately you have to place the pole and the 0 onto the complex plane, whether it is the S plane or it is the Z plane. By placing the pole, you have to design all the filter. And if you don't know how the filter response would look like, you will not be able to understand the the basic understanding of the filter design. Okay, so let us look into this. So what happens over here? So if you look over here, I have already written that it is a qualitative method. It does not give you any quantitative information. That means this should be the gain and this should be the actual gain or the phase response of the filter. And another important thing, it will only give you information about the gain of the system, that is modulus of Hs, and it will not give you information about the phase response of the system. Okay, now we all know that this is the S plane. Now this is a plane, so consider that this plane as a what you call as a table top. Okay, and on this tabletop I put a rubber membrane. Okay, I put a rubber membrane. Now what happens? So suppose this is the omega, this sigma, and this is the j omega axis. Okay, now when I place a pole over here, so what I said that if you look over here, this is the rubber membrane which has been fixed, this red shaded part. Then if you look from here, so what will happen? You will be finding that a cone like structure will be formed. Okay, so rubber membrane है, उसके ऊपर एक ये लगा दिया, so it will form a cone. Okay, now since it is forming a cone, so you are getting a slope like this. कुछ है copy? Okay. So you are getting a slope like this, right? Now you are getting a slope like this, but what you are interested in? You are interested in only how it is representing itself. This cone is representing itself on the omega axis. Now in the omega axis, if you check like this, if I place this pole, this pen over here, so this is my what you call distance or the height of the response. Okay, now if I move it backwards, now if you see the response, it has reduced. Okay, so this is what we have already discussed just now in terms of mathematics, that if we place the pole of the 0 near to the j omega axis, the effect would be quite larger. In this case, when we are talking about the pole, when we are placing the pole nearer to the j omega axis, we are getting a higher amplitude as compared to the situation when we are moving it away from the j omega axis. Okay, so this is what, if you see, we have seen. So you are having this base, and now we are interested in this part. Okay, so if you look, if you cut this response, so we get a response something like this, right? Now somewhere in the middle, if it is also encompassing the origin, so somewhere in the middle we will be having 0. If you see, this is the 0. So if this 0, it comes over here, then there is a small this thing carving. So there is a small carving over here, and then we are having 0 to omega 2, and from here to here we are having this one. Now if you start looking into this plane from this angle, what happens? You will be getting 0 to omega 2. You will be having a loop. So 0 to omega 2, you will be having the loop. And then at 0, there was some height. There would be some height. And somewhere it will go and die down. So we will be having some value. And at omega 2 again, on the other hand, you will be getting this thing. Now, when you have placed this pole near to the 0, what is happening? If you negate the negative frequency values, because we are not interested in the negative frequency values, so you get a response something like this. So what is this? This is nothing but a system which is allowing the low frequency components. This is nothing but a system which is allowing the low frequency component. So when we were kids, you used to play a game, right? So if you want to pass someone, you increase the rope height, and from the beneath, our friends, they used to pass, right? So the same thing happens over here. The pole, what it has done, it has increased the rope height. Now what is that variable over here? The variable is your frequency component, right? Now it is allowing the frequency components to pass through, but the thing is that it will not allow all the frequency components. It is allowing only the frequency components that are present in the range of 0 to omega 2. 0 to omega 2. Okay, 0 to omega 2, when we talk about this thing, these are nothing but a low frequency components. These are low frequency components, and just by placing a pole, what you have done is that you have designed a low pass filter. You have designed a low pass filter. Okay, just without knowing anything, without going into any of the mathematics, you have designed a low pass filter. Okay, similarly, when you talk about the high pass filter, where you should place the pole, you should place the pole somewhere towards the infinity. Okay, somewhere towards the infinity, if you place the pole, you will be getting the high pass filter. Then talking about the band pass filter. Okay, high pass filter, then band pass filter. So what you can do in the band pass filter, you place two poles. So somewhere, if you draw this thing, so if you look from here, so what you will be getting, something like this you are getting. So this forms a band pass filter because it is allowing only some frequency components in the region of omega 1 and omega 2 to pass through. Okay, so it becomes a band pass filter. Now suppose, if you see, suppose we have placed this over here and over here, say omega naught dash and omega naught double dash. So if you want this cutoff not at W1 and W2, and you want that the frequency response should come down very quickly just after the poles. What we need to do? We need to place क्या चाहिए? We need to place zeros. So what will happen? So this distance of omega 1 to omega 2, it has reduced further. Okay, so you have made a more stringent system. You have made a more stringent system. Okay, where the roll off is very quick. What is the roll off? Roll off is, ये देखो मान लो ये, if this is your average gain, a by root 2 is your cutoff frequency. Okay, suppose this is the cutoff frequency, say omega c. Omega c के बाद से ये कैसे, how it is dying down, how the response is dying down, it is called roll off. Okay, now if you place a zero near to the pole, so what will happen? The cutoff, the roll off, it will come down very quickly. The roll off will come down quite quickly. Okay, and if you do not place zeros on the frequency axis, roll off will be as per usual. Okay, so this is how you can modulate the thing. Now next is band reject or band stop filter. Okay, यहाँ पे हमने band pass लगाया. Now how to do it? You place two poles. Reject में मतलब it will stop some frequencies such that it will not pass through the filter, okay, or the system. So in between we have placed the zeros. In between we have placed the zeros. So this is band pass filter. Then notch filter. Notch filter means only one specific frequency will be stopped. Only one specific frequency will be stopped. So how this can be? So so you have the poles, you place the poles on either side, and at the specific frequency where you want to stop the frequency component, you place the zero over there. So it becomes your notch filter. It becomes your notch filter. Okay. So see, without understanding anything and just by understanding how we can place our poles and the zeros in the S-plane, we have designed all types of the filters. Okay, whether it is a high pass filter, low pass filter, band pass filter, band reject filter, or notch filter. Okay. Now, designing of low pass filter is one of the easiest thing. Okay, designing of the band pass filter, low pass filter is one of the easiest thing. Okay, we talk about high pass filter, especially in the case of say digital filters. What happens is that if we can design a low pass filter, we will be able to design many of the filters just like so. So you can design many of the things. So the first thing is low pass filter we have designed. So how to design high pass filter? High pass filter is nothing but वो तो है, but how can you design high pass filter using a low pass filter? Okay, simple ये है, if you look high pass filter plus low pass filter, if you talk about this thing, you get, अगर दोनों का if both of them they are having the same cutoff, that becomes all pass filter. and its response is 1. Okay, so 1 means you're taking the signal, then if you want to get the high pass filter component, 1 minus low pass filter, you get the high pass filter. Okay, so you have this one, then you have designed the high pass filter also. Why I am saying this? Because designing the low pass filter, if you look over here, if you want to design a high pass filter, how will you design it? Can you place the pole in the infinite? It's very difficult. So the thing is that if we understand and if we can design the low pass filter properly, it is quite easy, especially in the digital domain, to implement the other filters. Okay. So just now we have seen that if we have designed a low pass filter, we can use it to get the high pass filter response. Okay. Now we have band pass filter. Yeah, another important thing you should keep in mind that the cutoff frequency for this equation to be valid, you should have the cutoff frequency of the both of the filters as the same. Both of them should have same cutoff frequency. Okay. Now, suppose I want to design a band pass filter. Okay. So here what I have done, I have given low pass filter. First, the signal passes through low pass filter, then the high pass component it comes over there. So you get you pass it through the low pass high pass filter. So you get the band pass filter. Similarly, over here, what is happening? We are adding low pass filter component and the high pass filter components, and we are getting the output by adding. Now, how this is possible? This is possible because in the case of band pass filter, your omega low pass filter, that is the cutoff frequency of the low pass filter, should be greater than the cutoff frequency of the high pass filter. Should be greater than the high pass filter. If it is lower than, if it is the reverse, that means the cutoff frequency of the high pass filter is greater, then you will basically get nothing. How? Suppose you are having a signal 0 to 100. Okay, so your high pass filter is greater. Say for example, we are having 60 hertz. Okay, we take the example of 60 hertz. Okay, and this is say 40 hertz. So what will happen in either of the cases? So if we place first, take us the case of when low pass filter is the first, it is in the first instance, and then we get the high pass filter. So we will be having low pass filter. So this component, this will be passed, and this high pass component is already rejected. And when you are having this omega high pass in the second stage, everything is below this one. Above this one, everything is automatically rejected. Similarly, if you reverse this, that say, no sir, we will place the high pass filter first and then we will place the low pass filter first. So, at the first instance only, you are rejecting this low pass components. And then, when you are passing through the low pass filter, you are also rejecting this component. So you have to keep in mind when you are designing a band pass filter, then the frequency of the low pass filter, cutoff frequency of the low pass filter should be greater than the cutoff frequency of the high pass filter, and then only you will be getting this response. Through low pass filter you will be getting this, and through the high pass filter you will be getting this. So this white part, in both the cases they are rejected, and we will only get this shaded region, which would be the frequency region where the signal components will be able to pass through. The frequency components of the signal will be passing through, and thereby we are able to put or design the band pass filter. In the case of band reject filter, what happens? In this case, the case is different. Okay, you have to apply this logic. Your cutoff frequency of the low pass filter should be less than the cutoff frequency of the high pass filter. Okay, cutoff frequency of the low pass filter should be lower than the cutoff frequency of the high pass filter. So what will happen? And that's why we see we are giving the same signal to both the thing, and later on we are adding. So from the low pass filter, this component is coming. From the high pass filter, this component is coming, and then we are adding these two components to get a composite response of this one, wherein we are having a region where the frequency components have been totally suppressed. Okay, so you can see by designing a low pass filter, you can design anything, right? Similarly, when you talk about the notch filter, in the notch filter, it is a critical case of the band reject filter. It is a critical case of the band reject filter only where only a specific frequency is getting what you call eliminated. Okay, so if you do your mathematics correctly, then just by designing a low pass filter, you should be able to design the notch filter also. Okay. Now slowly we are getting into the mathematics. So I hope all of you know about this thing. What is this? So if you are given with a plus jb, okay. So you have the real axis, imaginary axis. So in the real axis we are having a, and b we are having this. So what happens in the first quadrant? Tan inverse of b by a. In the second quadrant, tan inverse of b by a plus pi. In the third quadrant, tan inverse of b by a minus pi. And in the fourth quadrant, tan inverse of b by a. So 1 and 4, they are same. And here we are having plus pi, and here we are having minus of pi. And you have to use your scientific calculators from the next class onwards. So bring your scientific calculators. So there would be some critical cases. Say for example, a plus 0i, when you are in the positive axis, your value is 0. When you are 0 plus ib, it is pi by 2 if you see. And if it is minus a by 0i, it is minus pi and minus pi by 2. Okay. And all calculations should be done in radians. All calculations should be done in radians. Okay. Yeah. So many of the things we have already discussed over here. What is Nyquist rate? Okay, we have already discussed. The Nyquist rate is nothing but Fs is greater than equal to O of Fm, where Fm is the maximum legal frequency in a given system. Okay. Now, if you look into the Z plane, the Z plane looks like this. So we already discussed. So we are having the 0 degree and also the sampling frequency over here. Okay. So 360 degree is nothing but your Fs, and Fm it lies over here. Okay. Now we already discussed that 0 degree and 360 degree, they overlap over each other. Okay. Now suppose I want to have a particular frequency component uh, identified where it is placed. Say for example, if your sampling frequency is 1 kilohertz, if your sampling frequency is 1 kilohertz, where would you place, or where would you find the 100 hertz? Where would you find the 100 hertz? Okay. Over here in the Z plane, which one is your frequency axis? Circle is your frequency axis. Okay, we are come into the Z plane. Okay, so your circle is your frequency axis. So frequency will be on the circle itself. So you basically have to find the angle. Okay, 1000 hertz, it corresponds to 360 degree. So 100 hertz, normal elementary mathematics. 360 by 1000 into 100, 36 degree में will be your 100 hertz. 36 degree में it will be your 100 hertz. Okay, so it will be somewhere over here. Now if you draw a line from here to here, okay, so that is the radius, right? Now if you place say poles or the zeros across this radial, then it is regarded as radial positioning of the poles or zeros. Radial positioning of the poles and zeros. क्योंकि हम across the radius we are putting the poles and the zeros. Hence, we call it as the radial positioning because we are putting it onto the radius. And whatever we discussed just now in S-plane, that holds good. If a pole or a zero is nearer to the frequency axis, their effect would be more. Okay, so there would be some question, there might come some question where you can be asked, what is the effect of radial positioning of the poles and zeros on the amplitude response of the filter? Then you have to explain in this way what happens if you place the pole at a point where the length is 0.9, 0.5 and say 0.4 or 0.3. Okay, the idea is 0.9 means you will be positioning the pole and the zero So you will be positioning the pole or the zero near to the frequency axis, then towards the mid, and another one towards the origin. So in this way, you are basically varying the distance of the pole or the zero towards the omega naught point. Okay. So in the S-plane, we have already discussed number of poles should be greater than equal to number of the zeros. Poles should always be on the left hand side and zeros can be placed anywhere. In Z-plane, if you apply the analogy of mapping, number of poles should be greater than equal to number of zeros. There is no change. Poles on the left hand side, we have seen that it maps into the unit circle. So inside the unit circle, zeros anywhere, no change. Okay, and talking about the frequency components, we already discussed that there is a many to one mapping. One point will be, one point can represent many frequency points. Okay. Now, with this knowledge, if you come into the Z plane, say same distance logic and all these things, just what we have introduced, we have just introduced an unit circle, and we know that frequency is on this unit circle. So our point P, what we were discussing in our last case, it is now be varying onto the unit circle. Okay, it will start from 0 and it will go up to Fm, which is pi. Right now, since we are in the Z plane, S is being replaced with Z. Equation remains the same. Again, if you see, if you look into the amplitude response, Bn, product of distance of zeros to the frequency point divided by product of distance of poles to the frequency point. Okay. Similarly, phase, sum of zero angles to the frequency point minus sum of pole angles to the frequency point. You're getting my point? No other difference. Everything remains the same. Now let us take an example, a numerical, wherein it has been given that our hz is equal to 1 by z minus 0.90 angle 0 degree. So we have to z minus this thing. This is basically a point. This is a complex point. But since it is 0 degree, so this is on the unit circle. Yeah, this is on the real axis. Okay, this is on the real axis. So our this equation, it becomes 1 by z minus 0.9. Now this equation, it will be used for determining poles and the zeros. When you try to find out the location of the poles and the zeros, then you have to see that the power of z, it is in positive. It is in positive. Okay, so from there we find in the numerator there is nothing, it comes out to be 0. In the denominator we get z equals to 0.9. so z equals to 0.9, where it is here. You're getting my point. Now we have plotted the pole zero plot. Okay, whenever you get this kind of equation, this kind of numericals, you have to um, uh, first plot the pole zero plot. Okay, now once you have plot the pole zero plot, then the next step or the next analysis or the numericals, it begins. Okay, also before going into the details, let us also take or create the equation or manipulate this 1 by z minus 0.9 this equation into an equation where we can implement the filter, because during the implementation we have seen we are only having three operators. First one is delay, second one was adder, third one was multiplier. So there was no component for z. So we have to convert this equation such that we have the delay. So when we multiply it, z to the power inverse by z to the power inverse, so we get this equation, and this equation is used for the implementation of the filter. Okay, for the implementation of the filter. Okay, so when we talk about the amplitude response, we need to find out at 0, pi by 4, pi by 2, 3 pi by 4 and pi. Okay, तो यहाँ पे क्या है this thing. So at 0 क्या होगा, we need to find out the distance. So this to this distance क्या है, total is 1, कितना आया 0.1. so your gain at 0 is 10. On the other hand, if you go for pi at this location, it is 1 by 1.9. 1 by 1.9. Okay, so uska karoge, you will be getting the thing. Now what about these three location? Pi by 2b, you will be getting it quite easily. How? ये पता है, ये पता है, you calculate the hypotenuse. Now what about the pi by 4 and 3 pi by 4? What about the pi by 4 and 3 pi by 4? Okay, so our 3 pi by 4 is somewhere over here. Okay, so if you look, कुछ बोलोगे? So this is one, क्या? हाँ, pi by 4. If you look over here, so we are having this thing. तो कैसे आएगा distance? You look over here, say this is the pi by 4 angle. Suppose this is the point, radius 1, this is total 1, this to this, so क्या है P by H, V by H, P by V, sine, cos, tan. What we are having? We have this hypotenuse and we have the angle. We have the hypotenuse, we have the angle. So using this sine function, we need to find out the perpendicular. You have to find out the perpendicular. Okay. So perpendicular का ये निकालोगे तो and also the base. ये cos से you will be getting the base. So you got the base position. इसका ये ऐसा ये आएगा. You got the base. Okay. Base. This is the base and this is 0.9. Right. This is base. This is 0.9. दोनों को subtract करोगे. So you will be getting this point. You got this point. You got the perpendicular through the sine. Okay. So you have got base and perpendicular. You have to calculate the hypotenuse. So that would be the distance. Okay. That would be the distance. Similarly, over here, this is 3 pi by 4. वो भी basically आपका pi by 4 है. So your base over here and base over here would be same. So this one plus 0.9 add हो जाएगा. You have the perpendicular. Now you calculate the distance of the pole to this point. Okay. So do it. We'll stop over here today.